What about the y direction? What about the y direction? Well, the net force in the y direction, there's no acceleration in the y direction, so that's equal to 0. The net force in the y direction this time, well, what do we have? We have n in the y direction is up, but we have friction in the y direction is down, and we have our mg, which is also down. So this time we have three forces. Since this is equal to 0, I can say sorry, pause. The n in the y direction, if you look at here, that's the adjacent side. So what I have is the net force in the y direction is equal to n cosine theta minus f. This time the y direction is opposite, so sine theta minus mg. And I end up with this statement that mg is equal to n cosine theta minus f sine theta. One of the things that we're going to have to deal with here, in the problem it says that under the best conditions here, it says that the coefficient of friction is equal to 1 Newton per Newton. What does that mean? Well, one of the things that we remember from our study earlier is that the coefficient of friction is a ratio of the frictional force to the normal force. That's an important statement. But if your coefficient of friction is equal to 1, that means that your frictional force would be equal to your normal force. I think this is going to be an important substitution as we work through these problems here, as we do our substitutions here. Because the question says, how fast could you go under these conditions? So again, we're solving for the speed. Okay, and if we're going to solve for the speed, I think we're going to need to know everything but that. So how do we go on from here? Well, one of the things that we can do is I can look at this, and if I solve for f, I may be able to substitute an f in here. And if I do that, maybe I can work my way through. So let's make this substitution in each of these and see if we can go from there. So let's take this one and move up here. So I end up with mv squared over r is equal to f cosine theta. Now it's plus n sine theta, but if the f is equal to the n, I can say that's plus f sine theta. And if I factor out my f, I have f cosine theta plus sine theta. This is looking a little complicated. Maybe it'll simplify in the end. If I do the y direction, I'm going to take this and just translate it over here. I have mg is equal to, again, if n is equal to f, I can say it's f cosine theta minus f sine theta. And if I factor out my f, I have cosine theta minus f sine theta. So here's the hard part. I have an f here and I have an f here, and I need to just need to get the speed, so I need to get rid of the f. So I'm going to solve for f here and I'm going to solve for f here and set them equal to each other. And let's see how that happens. So this f here is equal to mv squared all over r times cosine theta plus sine theta. This f here is equal to mg divided by cosine theta minus sine theta. And if I set those equal to each other, I get a new statement. I end up with mv squared all over r cosine theta plus sine theta is equal to mg divided by cosine theta minus sine theta. Now, I want to solve for speed. The m's magically disappear, and I end up with a weird term here. V squared is equal to rg cosine theta plus sine theta all over cosine theta minus sine theta. And when you plug and chug that, when I did it, I got speed is equal to about 77.5 meters per second. And that's with the best track conditions at 77.5 meters per second, and compare that to the no friction, which was 30 meters per second. And this is a pretty complicated understanding of this, but it really shows us how the friction can increase the speed that we can go.